So I'm going to start by giving you a basic rundown of what clustering is as a data science machine learning task. It's a task of an unsupervised nature, which typically means that it is harder to get, it's called an optimal results out of it than if we were working with a supervised task. And when I do my introduction, I'm going to talk about perhaps the simplest of all of the clustering methods, k-means. I know you've already implemented some k-means runs for your data. K-means is simple. It's complex enough that you can actually capture some of the things you might want to capture, but there's a lot of zenicroches, I don't know how to say this in English, a lot of pitfalls if it's not used properly. It makes it look, I mean, you get results that look like they could be the right types of results, but if you're not using it properly, the results are going to be meaningless. So that's going to give me a chance to talk about cluster validation. And that's really like the hardest part about clustering is in the algorithms in general, is how do you validate the results that you've obtained? And so that's going to give me a chance to talk about this a little bit. I'm not going to get into too much details about cluster validation because I'm going to revisit clustering validation next week when we talk about more advanced topics. Now, in my slides, I have hierarchical clustering for next week, density-based clustering, spectral clustering, and clustering validation. But we have already covered density-based clustering when we talked about anomaly detection, so I will not be talking about density-based clustering again. I just wanted to put it in the slides for the purpose of having a complete set of slides, but we've already covered that material. So today, clustering and k-means. Next week, hierarchical clustering, spectral clustering, and clustering validation. More in-depth look at these things. Okay, so let's get going. What is the main idea behind clustering? It's actually fairly straightforward. We are trying to find in a data set observations which are alike in some natural way or some natural sense. Now, I've taken the time to sort of give you air quotes around natural sense or natural way. It's actually quite difficult to describe what we mean by natural here. I'm going to modify a quote by a former Supreme Court justice when he was talking about smut. Here, it's very difficult for me to describe what a cluster is, but I know one when I see one. Okay, so we have, as human beings, this sort of evolutionary skill to recognize things that are alike and things that are not alike, things that are different from one another. So when you do clustering, what you try to do is to divide the data into naturally occurring groups. We also call them sometimes segment. So you might have heard of segmentation analysis. It's sort of the same approach. Now, these natural groups, when you look at the group, so within the group, the data points, the observations should be similar in some way, in some manner. And if you compare observations from one group to the next, the observations should be different. They should be dissimilar. And again, we have the ambiguity that's built into the words similar and dissimilar. What does it mean for observations to be similar and dissimilar? What does it mean for people to be similar and not similar? Or in your case, what does it mean for corporations to be similar and dissimilar to one another? It is an unsupervised task. You do not know ahead of time how many groups you will find in the data. Now, that's not entirely true. There are algorithms that specify the number of groups that you should be looking for. K-means, for instance, will look for K groups in the data. Now, you specify the value of K. So if you look for 3 means, it's going to find 3 groups in the data. But that doesn't mean that there truly were 3 groups in the data set to start with. So one of the challenges of using k-means is to determine, amongst other things, what's a good value for the parameter k based on the task that you're trying to accomplish. And that's actually a fairly difficult problem to solve. Now, to overcome that problem, we often design new algorithms. Like for instance, hierarchical clustering is an algorithm that you don't need to specify how many clusters you want to find. It's going to come up with a structure, and then you'll be able to read the number of clusters in the data set. But the problem now is that you've pushed the problem or the challenge to some other location, because when you do run hierarchical clustering, you need to find a distance metric, and you need to use a cluster linkage approach. We'll talk about that in a second as well, or perhaps next week. And that's an arbitrary decision, just as arbitrary as picking the number of clusters k and k-means would have been. And so with clustering in general, every time you come up with an approach to bypass a difficulty that you had in a previous approach, you sort of reintroduce a new approach. There doesn't seem to be light at the end of the tunnel. No matter what algorithm or clustering approach you utilize, you're going to have to make arbitrary decisions at some point. And that's at least from a scientific perspective, that's not great. Like, we don't want to make arbitrary decisions. We don't want our results to be the result of arbitrary decisions. But we can't really sort of overcome that challenge, that problem. One of the solutions is that you should never speak of the clustering algorithm or the clustering result for a data set. You never just run clustering once. You create a number of clustering schemes for the data using different approaches, using different parameter values within the approaches, and once you've created enough of them, then you can look at, for instance, pairs of observations. How often do they show up in the same natural group according to an algorithm? That's a little bit like what I've suggested you do for anomaly detection. You never just run one anomaly detection algorithm. You run multiple anomaly detection algorithms, and you see how often the algorithms output, a given observation as anomalous. And so you get to be anomalous, relative to the other observations, relative to the number of anomaly detection algorithms you've selected to run. It's the same idea. So I said you don't know. You can specify the number of groups you want to find in the data very often, but you have no guarantee that these number of groups correspond to the true number of groups in the data set. And so that's a hallmark of unsupervised learning. It isn't like saying, I'd like to predict whether somebody would be a good graduate student or not. I'm not going to try to make a yes-no prediction. I'm saying I'd like to find the groups in the data, help me find groups in the data. There could be 3, there could be 7, there could be 1, there could be none. You don't know. Okay? And that makes the job even harder. How do you determine if you found the right clustering result if you don't even have something to go back to and compare to say, yes, this was a true answer, this was a true value. You don't have that. It's unsupervised learning. So the validation process has to be relative to what it is that you have found, as opposed to relative to some training set or some true answer key that you can look at afterwards. Very often we will use the idea of distance to measure similarity. So when observations are close to one another, we'll say that they're similar, and when they're far from one another, we say that they are dissimilar. But we talked about this when we talked about anomaly detection as well. How do we define the distance? It isn't just a question of measuring the physical distance between points. That doesn't always make sense. What's the distance between a 45-year-old man and a 4-year-old girl? How do you measure distance for these types of observations? So in all cases, if you're going to be using distance to stand in for similarity, you need to have some idea as to how to compute the distance between observations. And there's an awful lot of behind the scenes work, and again, arbitrary decisions that need to be made before you can come up with a distance that's going to please you to some extent and work with. Now, I've shown you this slide before when we talked about density-based clustering. Ideally, you would look at a data set like this, or at least a two-dimensional projection or representation of the data set, and even if I hadn't colored the points in red, blue, green, and gray, you'd look at this and you'd think to yourself, yes, it looks as though there's three groups of customers here, and a bunch of customers that don't seem to belong to groups. Naturally, this is how we view this data set. So this is something that human beings can do fairly intuitively. Like, we're pretty good at facial recognition, for instance. This is something we do without thinking about it, at a subconscious level. This whole idea of searching for patterns. Again, a lot of people think that this is an evolutionary holdover. You know, in order to survive in the wild, we had to be able to recognize when something was going to be likely to lead to some danger for us down the road, and we become very good at recognizing patterns. So people are very good at dealing with messy data. Computers and algorithms have a harder time, and part of the challenge, again, for the computers and the algorithms, and for us when we write algorithms to be run on computers, is that human beings, we never have to validate our results against the true answer. There's no such thing as a true answer. And algorithms basically need something to evaluate how well they perform. And this evaluation is done for us internally without really thinking about it. There's no agreed upon definition of what constitutes a cluster. I may not be able to define what a cluster is, but I know one when I see one. I think most people would agree here that they see three clusters. And then based on this projection, you might say, well, a cluster is going to be a group of observations, perhaps where they're close together, they're very dense together, and they're distant from other groups. And that might work in some cases, such as this one, but it's not too difficult to come up with cases where this would not be a sufficient definition. And I'll show you some slides afterwards where we have examples of things which should probably be considered clusters, but don't match this definition here. And that's a real challenge. There's no definition of what a cluster is that works in all cases. So a lot of the time, in order to be able to get good results from our clustering algorithms, we build these fairly complex processes and fairly non-intuitive. I'm going to talk about spectral clustering next week, which is basically an offshoot of graph theory. And it requires you to build something called the Laplacian of a graph. And then you look at the multiplicity of an eigenvalue related to this Laplacian, and that tells you how many clusters there are potentially in your data set. So great, from a mathematical perspective, this is sound, but it defies any sort of intuition. Right? So we come up with algorithms that find these clusters to try to recover what it is that our brains do without thinking about it. And we have these very complex processes, but they probably don't actually map to what it is that we do, even though we might get similar results. And that's not great. Right? One of the other challenges that we have is whenever we run an algorithm on data and we get clusters, there's a very strong temptation to explain why the group that we have is part of a cluster. So I call this explaining it a posteriori. I remember this anecdote that one of my profs had told me when I was still at school. He had attended a conference at Johns Hopkins, I think, University in Maryland, famous medical school, and the speaker had gone on and played back. It was back in the days where you had these acetate. There was a projector and you put a little. What is it? Sorry?
Dactylos.
The dactylo, something like that. Back in the day, when you had a projector, you put a transparency. Yeah, you put a transparent sheet on the projector, and you could see what you'd be able to project, and you could talk to that slide. So the presenter had put the slide down, and then shown this. I forget what the details of the anecdote were, but shown these results based on the number of medical tests. And then I'd thrown it back to the audience and said, well, what do you think you're seeing here? And you had all these eminent medical specialists. Oh, yes, what we're seeing is this and this and this and that. But it turns out that he had actually, by mistake, put the graph the wrong way up and down. And so the chart was the opposite of what all these people had managed to try to convince themselves they were seeing. Right? And clustering is, you're not going to make mistakes. But whenever you see the results, you feel like explaining what it is that you've seen. And because a lot of the algorithms are completely complex, non-intuitive, that's a mood exercise. All right. So the exercise of trying to explain what it is that we're seeing, and then hence labeling the group of observations. These are the corporations which we think are, I don't know, you come up with some sort of description for that group. Once you've labeled the cluster, then that becomes your definition for the cluster, and that's a misleading thing. You give it more power than it truly has. So you have to be on the lookout for that. That's a big challenge with clustering. Another issue with clustering algorithms is, for the most part, they tend to be non-deterministic. Which is to say, you run the same algorithm twice on the same data set, and you might actually get completely different results. The order in which the data is presented or found in the file might also affect the results. And, depending on the algorithm, you might have what we call starting configurations. If you have different starting configurations, you might get different results. So, what does that mean for repeatability? How do you explain to your supervisor that they need to do, take a specific action based on what they've seen? If when you try to run the algorithm again, you get a completely different result. Right? Well, the solution here is clear. You never run it once. You run it multiple times over, and you see if there's some sort of distribution to which the results of each of the runs converge. And that gives you a bit of a probability argument for doing stuff. But you never just run it once, because the majority of the algorithms that you could run are non-deterministic. In order to do clustering, no matter what algorithm you use, you will need a measure of similarity, which we typically call W, or a distance between observation D. Now, you need a distance because if you're going to be using distance as a proxy for similarity, observations that are close are similar, observations that are far are dissimilar, so you need to be able to measure the distance between observations. But the true requirement is the similarity, because you are building similarity off of the distance, right? You're concluding whether things are similar or not based on whether the observations are close to one another or not. So you need a distance to build a similarity between observations. There are other ways to measure similarity that do not require you to have a distance. But in either cases, you need to have some measure of similarity between observations. Now, typically, we sort of restrict ourselves to three types of distances. Euclidean distance, the distance as the crow flies, I believe is the English expression. Straight line distance. the cosine distance, which measures the angle between the vectors. So this would be the origin, this would be where the observation is found, and then you just look at the angle. And if the observations have a small angle between them, it means that they're pointing in the same direction, and so they are similar. The similarity is the direction in which they're pointing. This is often the similarity that is used when you're working with text data. We have something called the Manhattan distance. All of these we've talked about when we talked about distances in anomaly detection, but the Manhattan distance basically computes the distance that you would have to drive to get to, from two points in Manhattan on a grid. Now, you can imagine that you have, points in 10-dimensional space. It wouldn't be a 2-dimensional grid, it's a 10-dimensional grid, but it's the same sort of idea. And no matter how or what measure of similarity or distance you use, you should in general make sure to transform the data, to center it, to normalize it, so that if you're trying to compare ages for one of the variables with number of employees, like the ages of the corporation, and number of employees, if you have a corporation with 1,000 employees and one with 950, the difference is like 50 employees. But if you try to compare now the age of the corporation, perhaps one of them was incorporated in 1980 and the other one was incorporated in 1995, then the difference there is 15 years. Well, how does 15 years compare to 50 employees? Apples and oranges. So you need to find a way to basically scale everything so that the differences are comparable. Okay. Now there's other types of metrics, and based on what you've described in your email at Quebec, you probably want to do something other than using Euclidean distance for your measurements. And so if you have mixed data, there's combinations of things you put together. You build a new distance whenever you have categorical variables and numerical variables, and based on the type of numerical distance you found, then there's a specific categorical distance that you should use as well, and vice versa. So we can talk about this a little bit later as well. What do people use clustering for? Well, in general, like you can look at, for text documents, trying to group documents that are similar according to their topics. So topics analysis could be a way to do this. And the topics are determined by finding patterns of common and unusual words in documents. So you basically cluster documents into topics based on how the words are used within the document. So that's one way to use clustering. Product recommendations, these tend to be cluster-based algorithms. So if you go on Amazon and they know what your history of purchases is, they know what the history of purchases for everybody is, and they've identified customers that are similar to you in their purchasing habits. So you've been clustered with other customers, and then their recommendation engine is based on, well, these other people have purchased these products. We find that you're similar to this person. You might be interested in these products. Or these other customers have purchased and enjoyed these products. We find you to be like these other customers. You might enjoy these products. So you can cluster customers together, but you could also cluster the products. So products are similar if they're being purchased by similar individuals. So you can play it the other way around. Right? In essence, what's happening here is you're flipping or switching the rows and the columns in your data. And that's something that could be useful for some of your eventual work. Marketing and business, people usually try to segment their clients based on profiles of demographics and preferences. That's a little bit what you're trying to do with the corporations here, segmenting the corporations based on a number of variables. Look, I can come up with more examples, applications. There's no need to sort of really push for this. There's just a lot of applications, a lot of reasons why people use them. But I need to point out that just because we've identified two customers as being similar according to their purchases and likes, it doesn't mean that the recommendation that they will make is going to be the right recommendation. It could be that you already have this product and you don't need to purchase it again. It could be that actually you were very like this person in many ways, but in some very important ways you were unlike. So there's no guarantee that you're going to be able to produce the right answer, the right kind of cluster with your algorithms, right? A lot of it is, well, serendipity, chance. Okay. One of the main reasons why we do use clustering in data science is if we're dealing with a big data set and we'd like to accomplish some sort of supervised task. Perhaps make a prediction about whether this is likely to be a fraud-filled entry or not. Well, we might say, I have too many corporations, they're way too different from one another. Let me cluster them in smaller groups that are somewhat alike, and then I can use a different approach on all of my groups and all of my clusters to accomplish another task that I have in mind. Okay, so clustering in itself is rarely the end result. Like, you're using clustering to simplify the task, divide and conquer in this case. Right? Divide your data into smaller groups and then possibly use a different approach on each of the smaller groups to accomplish the true task that you have in mind. Typically, this is what the pipeline or the process looks like. You start with a data set, you have all of the observations, you feed the data into a clustering algorithm that builds a model. The model will provide you with a cluster assignment, which then you will feed into some clustering validation routine or approach. And the clustering validation could be as simple as, does it pass the eyeball test? Do the clusters look reasonable or not to me as an expert in this field? It could also be that you do have external validation. If it's available and appropriate for you to use it, you might be able to use it. But typically, because you're not using the external information to build the model, there's no guarantee that the cluster assignment will align with the external information that you have. We'll do an example later where we talk about the infamous iris dataset. And the dataset, there's 3 types of flowers, and you can try to cluster it. And you'll find that you can come up with cluster assignments that match the actual species of the irises, of the flowers. But that's just an accident, because you could have collected other data about these irises, not just their actual species, but also perhaps the date when they were collected. That's external information which isn't used to cluster the data, just as the species of the flower wasn't used to cluster the data. And if you had used the dates instead of the species, you would have gotten absolutely no alignment between the type of flower and that external information. So you don't know ahead of time if the external information you have to compare it with aligns with what it is that you're trying to find, or what the algorithm is trying to find. So it's a bit risky to use external information to validate the cluster assignment. Either way, however you decide to assign your clusters, and here, quite conceivably in this clustering algorithm, you're running multiple clustering schemes, and you're joining them in some sort of ensemble model to create a final cluster assignment. But this cluster assignment here might be the result of multiple runs. If you're satisfied as a subject matter expert, and then you need subject matter expertise here, without subject matter expertise, the validation isn't going to be worth a hill of beans. If you're satisfied with the clustering validation, then you could deploy it. But now comes a difficult problem to answer. I've used my entire data set to build this clustering assignment. You come up with a new observation which is not part of the data. To which cluster do I assign the observation? That is not an obvious problem to solve. You could decide that your cluster assignment here becomes a training set, and then you're going to use a supervised learning method to associate the observations to a specific cluster. That's not the stupidest thing you could do, but if you're doing this, you're stepping outside of the clustering algorithm. It is very difficult to update your cluster assignments when new data comes in. So this is typically a problem in a field that we call data streams, right? When new data comes in, old data becomes less meaningful, less significant, and you have to update the results without necessarily rerunning the algorithm on all the data from scratch. So we have ways to update results, part of data streams, as I said, not something we'll talk about. That's a fairly technically complex topic, but just be aware that once you found clusters, well, the presence of new data might actually have changed what the clusters would have been. And so you have to be smart about updating your clusters in general. Okay. Again, not to belabor the point, that's a very difficult problem to solve, or to work with, or to come up with a pleasant solution. The last time I checked, I think there were easily 100 different clustering algorithms out there. The ones that are more often used, like the workhorse algorithms, k-means. That's the one people use. When people tell you they do data science, typically, at least up until very recently, what they meant is that they either run a decision tree or they run k-means on their data. Right? So k-means is the one that basically everybody uses. It's classical. It's a classical model. It's a well-defined model, and very often it's going to give you the types of results that you might look for, thanks to the central limit theorem. Data is distributed in general in such a way that the types of groups that k-means is well designed to find usually exist in data, or very often exist in data. So k-means is not like a mistake to use. It's just that very often it's used when it shouldn't be used, because that's the only method that people know about. It makes some pretty stringent assumptions about the shape of the clusters. If you're going to be running k-means on your data, what you're really assuming is that all of the observations that are similar congregate in blobs, like what we've seen here. It could be that the blobs are in multiple dimensions because you have more than two variables, but that's basically the idea behind k-means. And there might be good reasons to expect that to be the case. But there could also be reasons why that shouldn't be the case, especially if you're dealing with mixed data types. If you have text or categorical variables, what does it mean for things to be a blob if you're working with categorical variables? That's not obvious at all. Other types of algorithms that are used, hierarchical clustering, is just basically the equivalent of a decision tree for clustering. Very easy to implement, very easy to provide an interpretation. It has the advantage of being deterministic. A lot of good things for hierarchical clustering. We'll talk about some of them later when we do talk about hierarchical clustering. You still have to come up with a distance, but you always have to come up with a distance measure or similarity measure, so that's not a problem. A linkage strategy, that might be hard to come up with. Why isn't it used all the time? Well, it's excessively computationally expensive. So it's expensive, and to be fair, typically doesn't give you very good results. At least people are very often unhappy with the results. That's the reason why you might not want to use it. Here's a very popular approach nowadays, because people who do topics modeling and natural language processing would use it, latent Dirichlet allocation. But I gotta say, from a mathematical perspective, this is a complicated thing. Like, this is something you would teach to graduate students after they've taken like pretty much every other course that they could have taken. It's not intuitive at all how it works. It's a generative model, and it's a real pain in the backside to explain. Same thing goes with expectation maximization. Like, these are popular models, and you can run the model without really knowing what is under the hood or what goes under the hood. But since you have to make arbitrary decisions, if you don't know what goes under the hood, you don't know if the arbitrary decisions you're making are actually going to be helpful or will hinder you in your path to getting what you want out of things. Like, hierarchical clustering would produce objects like this. The observations are the leaves of a tree, and then you sort of combine them together into branches. And then you would decide where you cut the branch or where you cut the tree. Shake it loose, and you'll get 4 clusters in this case. Okay, we'll talk about how you would build such a dendrogram in the future. Other things, birch, I won't talk about it. It's an older approach. Dbscan, I've already talked about it when I talked about anomaly detection. Affinity propagation, that's a neat one, because you don't need to specify how many clusters to look for. It's going to go and find the number of clusters. But it does so, unlike density-based spatial clustering, Dbscan, by literally going through a bunch of options and afterwards picking the option that gave you the best results. And that's still fairly arbitrary, because you have to come up with some metric to determine which one of those is the best one. And that's completely arbitrary. Spectral clustering we'll talk about as well. Technically more complicated. We like it because it helps you recognize clusters that are not blobs. And that could be something you're interested in finding as well. So Dbscan, for instance, would work like this. I've shown you this example before, so I'm not going to talk about it too much, but what I like about spectral clustering here is it would recognize in this spiral data set that there's 2 types of points, right? There's the points in the black arm of the spiral, and there are the points on the red arm of the spiral. And here, I mean, look at this red point right here. Oh, you won't be able to see it this right. Sorry. Look at this red point that's right here. It is closer to a black point than it is to another red point. And yet, we believe that this red point has more in common with this more distant red point because they belong to the same shape, right? What they have in common is this sort of continuity of being part of an arm. Spectral clustering is equipped to recognize things like that, which k-means would never in a million years be able to find. Density-based clustering might, but it would be likely to fail at recognizing the things, depending on what we use as a neighborhood for the things here. So k-means, which we'll talk about for the next little bit here, very well adapted to numerical data. You can also use it for categorical data. There you would be using k-modes instead of k-means. And there are variants of k-means. You can have k-medians. You can have k-means parallel. If you're working with like big data sets, there's a lot of variants, but it's basically always the same idea. Well adapted to numerical data, but it will typically force your data to cluster into groups of roughly the same size, even if the data doesn't support it. But as a first pass, it's still not a bad approach usually. How does it work? It's easy. We're going to try to pretend we want to do 3 means here. So we're going to try to find 3 clusters in our data. And often this is a number or a parameter value that would be arrived at after discussing it with the subject matter experts, people who know the data inside and out, who have intuitive experience with it. So let's say it's 3 means. So we have a data set and we want to find 3 groups of observations where, the observations will be somewhat similar within the group and dissimilar to other observations outside the group. So how does it work? You've selected your number of clusters, K. You are going to start by randomly selecting 3 of the observations as your initial cluster centers. Now, if you have a lot of observations and you pick 3 of them at random, perhaps you'll get, 1 way over there, 1 over here, and 1 at the bottom. That could happen. But it's conceivable that you'll get all 3 of them in the same corner. You're picking them randomly. Now, if you want to speed up the process, you might make it so that you pick the first one randomly, then you pick the second one randomly, but with a restriction that says I'm going to try to be as far away from the first one as possible. That's something you could implement as well. And then you can try to maximize the distance between all of the points. That would speed up the process to some extent. At any rate, you've picked 3 instances randomly. And now this is the first instance where the stochastic nature of the algorithm comes into play. If you pick 3 different points randomly than I do, it's conceivable that we will not converge to the same 3 natural groups. Okay, in either case, you have picked 3 points. Now what you're going to do is you're going to compute the distance of every point in the data set to each of these 3 points. So if you have n points in the data set, you need to compute 3 times n distances. That is not super costly. This is something you can do quickly with machines. Right? That's order n in the complexity of the operation. Once you've done that, you will take every one of the instances. So for each instance, I'm going to have a distance from the first point, a distance from the second point, a distance from the third point. I'm going to assign each of these instances to the point that it was nearest to. So at the end of my first pass, every single point in my data set has been colored, let's say red, green, or blue, according as to whether it was closest to the first point red, the second point green, the third point blue. Okay, so now every point has been assigned to a cluster. Is this it? Is this the end of things? It isn't, because we picked these initial points completely at random. We don't know if they correspond to natural groupings. So once you've done this, since every point is either red, green, or blue, you're going to take all of the points that are red and you're going to find their center. You're going to compute the mean of all of the variables for all the points that are red. And in effect, what that has to do is it basically takes your red points and it finds a representative for the red group. Do the same thing for the green group and the blue group. Now, when you compute the center, there's no reason for that center to be one of the observations in the data set, especially if you're working with numerical values. It's going to be some geographical center, if you want. Now, so we don't call it an instance anymore. We call that the centroid. So now we have 3 centroids in the points in the data set, which are basically the center of each of our clouds: red cloud, green cloud, blue cloud. And now we repeat the process again. Because we have 3 points, 3 centroids, and n observations, we compute the distance of each observation to each of the 3 centroids. And once that's done, we assign this observation to whichever one of the 3 centroids it was closest to. Now, there might be some movement. It could have been that after the first pass, a point had been assigned to the red cluster, But now that you've recomputed the centroid, that you've shifted the centers, that red point isn't red anymore, it's blue. So there's going to be a little bit of jockeying in the different clusters. You repeat the process until there's no more transitions, until the points stay always in the same cluster, which is to say until the centers don't move around anymore. They converge to specific locations, until the clusters are stable. Graphically, this is roughly speaking what it might look like. You might see some movement of your centers when you compute the centroid, and you're going to keep that up until they don't move anymore. So here's an illustration of this. You start by picking 3 points. Well, there's variants of this algorithm where you don't pick instances to start with. You just randomly pick centroids and then you move from there. And this is what's happening here. I've picked 3 points. You assign the colors. So the points in blue here were the points that were closest to the top X. The points in red were the points that were closest to the bottom X, and the points in green were the points that were closest to the rightmost X. And then I compute the new centers, and I'm seeing that there's a movement of the X's. And you continue until you get 3 sort of clusters in your data. If we're assuming we want 3 clusters. And if you look at iteration 7 based on the original data set, that sort of makes sense. There's a few points where it's less obvious, like this blue point here and this green point here. Perhaps they shouldn't be assigned to a cluster. I mean, they're assigned to a cluster because we have to assign every point to clusters, but perhaps that shouldn't be, it's not a necessity, not necessarily something you should do. At any rate, that's the process. And it's not any more complicated than what I just described. Yes, there are variants to speed up the process. And look, you can decide to use a different measure of distance, right? When I say you compute the distance between each point and the centroid, well, whatever distance function you've decided to pick could be useful here. It could be something that would modify things, but no matter what distance you pick, that's the process. And it's quite simple and it's efficient, and we know how to speed it up. All of this goes towards explaining why K-means is so popular. This is something that I could take my 17-year-old child and spend enough time with them, and they would probably understand the concept, the principle. This is not a sophisticated algorithm. It's not always easy, though, to guess how many clusters there should be in data. I'm giving you here a data set of only 2 variables. I'm going to ask you, how many clusters do you think exist in this data set? What do you think? It depends. It depends on so many things. If I take off my glasses and I take a few steps back, and I squint, I see 2 clusters. Actually, that's not true. When I squint, I see 3 clusters. When I don't squint, I see 2 clusters. If I'm very close to it, I think I only see 1 cluster. It really depends on what it is that you're looking for. Now, let's say there were 3 clusters with this data set, and you could pick starting points, random starting points, and you see there might be a fair amount of movement, forgive me, before you end up converging to stable clusters. So here, if we decide that there's 3 clusters and we throw k-means at it, it would find these 3 clusters. That's not the cluster that I saw when I walked back, took off my glasses and squinted. What I saw there was instead the first cluster that contains the red points and a few of the black points right up here. Then I saw most of the black points here and then the blue points separately. Was I wrong? That's not a question to ask. Or at least it's a nonsensical question to ask when you talk about clustering. Was this the optimal clustering scheme or result? It depends. And look, if you find it frustrating that whenever you run your clustering algorithm, you only know if you're right, modulo it depends. Imagine what it's going to be like for the stakeholders or the people above you in the business organization that don't have the quantitative background. This is an unpleasant thing to report on, right? So, something to keep in mind. We'll take a little break now, and when we come back, I'll talk about the strengths of k-means, some of the limitations. I'll show you an example, and I'll talk about some of the ways in which you can validate, at least internally, the results of your clustering thing.